Thank you very much for the invitation. I would like to describe a bit this conjecture which concern the geometry representation of the fundamental group of a curve, and in particular describe the contribution to this conjecture of our project. So the main character is the character variety. So I will denote it in this way, or briefly just MB. And this is the space of representation of the fundamental group of CG. For me, CG is a smooth projective curve over C of genus G. Inside some reductive group, and it will be just GLN and SLN in the following. And we will say that two representations are the same if they are conjugate to each other. So when we parameterize it, we will quotient by the action of conjugation. And this space are called character varieties, or also Betti moduli space. You see, Betti is topological. We forget about the complex structure of the curve. We remember just the topology. So in non-abelian Hodge theory, there is a way to package the information of this moduli space in another moduli space, often called the Dolbeault moduli space. I will use here a picture to represent this moduli space, which comes from a picture of Simpson. He represented this space as boxes without the lid, to emphasize that these are open varieties. And I will call this MB. And there is this other moduli space, M-dol, which is the moduli space of GX bundle. So today I will focus more on this moduli space. The only things that I want to mention is that there is an homomorphism between these two. But actually, this is not an algebraic isomorphism. The algebraic structure of these two spaces is very different. So you can see here from this description that this space is affine, while this other space actually carry a proper vibration, the Itchin map, over an affine space. So in particular, this space is fibered in proper, generically Lagrangian tora, but they are proper algebraic subvariety, but this space can't. So this is not an algebraic isomorphism. The content of this conjecture is try to understand better this correspondence, and especially to understand his asymptotic behavior. So what happens outside a compact subset? What does it mean? What we can do here is try to compactify these spaces, emphasize that they are not compact variety. And since the algebraic structure are different, also the topology of their compactification will be different. Usually to compactify M-dol is enough to introduce a single irreducible component, maybe with some orbifold point, while MB requires a lot of irreducible components at infinity. What we can do now is finding some tubular neighborhood of this divisor. I call it N dol, and then puncture them. So I mean that I remove the divisor. You see, what I'm taking is the complement of a compact set. Okay? And I can do it here in the same way. And V star. Okay? So through this homomorphism, we have a map from N dot star and B star. Can be an homomorphism, or I mean, they can be homotopic equivalent. And we can choose N dol in such a way that this structure of fibration is saturating this set. So we can think of projecting this space to AN, but in this way we avoid a compact subset of AN. So composing with a radial projection, actually we can map this space inside a sphere of large radius, if you want. So we have a map here in this direction. So we said that there is no proper algebraic map of this type on this other part of the correspondence. And the conjecture gives an idea of how we can recover in an algebraic way this sphere on the other side. What should correspond to this sphere on the other side? And the conjecture said that this should be the dual boundary complex of MB. So let me define what this object is. So in general, the dual complex of a simple normal crossing delta. So this is a divisor or just a simple normal crossing variety, and these are the components of it. I mean that each of these components is smooth and they are meeting transversally. Actually, we would like to allow some mild singularity, so we should say better divisorial log terminal variety, so DLT. But you can pretend that they are just simple normal crossing. And what is this object? This is a regular cell complex. So if you want a CW complex, and when I give a CW complex, I need to prescribe his skeleton. So the zero cell of this CW complex will be in correspondence with the delta I. The K cell will be in correspondence with the irreducible component of delta I0, delta IK. So let me do an example. Yeah, maybe let's write here. So let's start from one of the easiest character variety that we can imagine, C star times C star. So what is this object? So to build the dual complex, we need first to produce a simple normal crossing divisor. So the idea is that we would like to compactify this space. One way to compactify it is to compactify to P2, adding 3 lines, okay? Now, we have 3 lines, so to each of these lines, we will have associated a 0 cell. And since each of them intersect, we will draw an edge joining them. And you see that actually, this is a dual graph, and dual complex are generalization in higher dimension of dual graph. This is actually isomorphic to S1, okay? That's what we wanted in the conjecture, to see some spheres appearing. But you could object and say, why you choose P2? We could have chosen other compactification. Suppose if you take a point here and you blow it up, so this becomes the blow up of P2 in one point. Well, you see that the dual complex now becomes something like that. You add an edge. And this is no more an S1. But you see that in any case, the homotopy type doesn't change. And this indeed is a general statement of Stepanov. So if U is an open smooth variety, then the homotopy type of the dual boundary complex of U is an invariant of U, which means that it doesn't depend on the choice of the simple normal crossing compactification. For instance, the rational homology of the dual complex becomes the 0 piece of the mixed Hodge structure of the simple normal crossing divisor. Actually, I say that we should work in a singular setting. So actually, if U is an open variety with Q factorial and KLT singularity, you can take here DLT compactification. And the result still holds thanks to the work of Defernay, Collard, and Xu. So why am I emphasize the fact that you need to work with singularities? Well, because most of those varieties are not smooth. So we have this immediate problem of not being able to construct a simple normal crossing compactification. And consider these varieties are affine, so if they don't have isolated singularity, the singularity really goes at infinity. There is no way to avoid them. So let me remark that DLT compactification do not appear in the original formulation of P equal W, but they are essential if MB is singular. In particular, we know that, and they exist, this DLT compactification, if G is GLN and SLN, so you need to use the DLT blow-up of Haken and also a result of Bellamy and Schedler. which granted that actually these character varieties has this property that they are cofactorial and KLT. Okay, so I probably need again that blackboard. So you see here I wanted to construct something on the side, on the Betty side, which should recover this sphere on the Dolbeau side. And indeed, the conjecture of the geometric equal W conjecture, which is formulated by Kazarkov, Knoll, Pandit, and Simpson, says that actually this diagram should be completed and that this map should be an homotopy equivalence. And that this diagram should commute up to homotopy. So this object is just defined up to homotopy. So that's why also in the conjecture we see just statement in homotopy. Okay. So what we know about this conjecture? Yes.
Does this imply the statement of the first case was a conjecture?
This is a small digression, but at least this is a really nice question. Could I answer at the end of the talk? The brief answer is no, but just partially. Okay. So what do we know? So here I formulated the statement for character varieties, but a priori could apply also to twisted character variety, maybe some parabolic character variety, some Penlevé system. Well, what we know is that, well, if we consider the easiest case, so when G is equal C star, then if you look at this definition, this is abelian, so also this map factor through the abelianization of the fundamental group, the character variety is just C star to the 2G. And now the dual boundary complex can be easily computed. You can compute it in the same way we did in the case of P2. Okay, take any toric smooth surfaces which compactify these torus, and if you take the cone over the dual complex, you recover the fan of the toric variety. The toric variety is complete, is the whole space, so this needs to be a sphere. Then there are other cases when G is SL2, and we are not really in this setting, but C is P1 minus K point. And if you fix the traces at the puncture of these surfaces, actually you can get a result in this direction. And for 5 points, K equal 5, this was the result of commu. And for K greater than 5 by Simpson. And they proved that actually the dual boundary complex as the homotopy type of a sphere of the right dimension is not important for the moment. And in that paper, Simpson asked whether it's possible to determine the homotopy type of the dual complex of character varieties of projective curve, so compact curve. And in our work, we establish it for elliptic curves. So our main theorem is that the dual boundary complex of M1G is PL homomorphic to a sphere of dimension 2n-1 if G is GLN, and a sphere of dimension 2n-3 if G is SLN. And actually we prove a stronger result because I said that this is a PL homomorphism. So I just exhibit to you an example where here, where actually it's not clear what should be the homomorphism type of this object. But the idea is that you could try to restrict it to spatial compactification and obtain dual complexes that are now defined up to homomorphism. So the stronger version of the geometric P equal W can be achieved by restricting to so-called, so I told you that we need to allow some singularity, so DLT, and we would like to take a minimal compactification. Now, minimal in this context should be local Abiyao. It's conjecture that all character varieties should admit local Abiyao compactification, and is known in rank 2 by a result of Wang. But it's not clear if it's DLT or log canonical. I just recall that log Calabi-Yau means Calabi-Yau up to a perturbation. So the canonical class of a compactification of MB plus its boundary needs to be collinearly trivial. Okay. So I would like to give an idea of how you can prove such a statement. We have two proofs of this statement, one in the relative and the other in the absolute setting. And I would like to describe the proof in the relative setting. So explain an argument of degenerations, degeneration of hyper-Kähler manifold. And I will explain why hyper-Kähler. So the idea is that we would like to prove that the character varieties M1 GLN and M1 SLN are limit, in a suitable sense, of Hilbert scheme of K3 surface or generalized Kummer variety. So what does it mean, limit, in this context? Try to make a rigorous definition. So we mean that there exists a degeneration f from chi to the germ of a curve So this is a germ of a curve, so it has 2 points, a geometric point and a generic one. So on the generic point, so the generic fiber is one of the hyper-Kähler that I mentioned above. Is one of these hyper-Kähler manifolds. And two, the special fiber that will have DLT singularity, think of simple normal crossing if you prefer. On the special fiber, x0, there will be a lot of irreducible components. But there will be a distinguished, let me raise it a bit. There will be a distinguished component delta 0 that is somehow related to this character variety. So such that the pair delta 0 delta I, so the pair given by the variety delta 0 and a divisor in it given by the restriction of all the other irreducible component in the fiber restricted to delta 0 is Krepan birational to a compactification of MB. So really here you need to think that delta 0 is a compactification of MB in first approximation. What does it mean, Krepan birational? For us, the only thing that we really care is that the dual complex of this boundary is PL homomorphic to the dual boundary complex of MB. So you see that we recurse the problem of computing our dual complex in terms of the geometry of this degeneration. So how we can get the statement of the P equal W conjecture? So the first things to prove is that there exists such F with the property that the dual boundary complex of what? Of the central fiber is CPN, a complex projective space. And the second thing to prove is that this is a kind of easy statement in simplicial topology. If d delta is a PL manifold, then d of the sum of delta I restricted to delta 0 is a PL sphere. But now you see that if I put together these results and the property of the degeneration, that this space is actually the dual complex we were interested in, we get the geometric P equal W. Okay, so let me explain briefly these two cases. So let's start from the second proposition that is kind of the easiest one.
Something like this expected in any genus?
What do you mean? What is expected? Yeah, that's the claim. That's what I would like to end the talk saying. Can we construct the degeneration for any genus? Who should be the candidate here? Probably moduli space of semi-stable sheaf over K3 surface or abelian surface. Great. So, where this comes from? It comes from this observation. We need to understand what is the relation between these simplicial complexes. So this object is often called the link of V delta 0 in the dual complex of X0. So V delta 0 is the zero cell which corresponds to the component delta 0. And the link is the boundary of a neighborhood of V delta 0 in D delta 0. I think that is better to do a picture to see what's going on here. So suppose that this is our dual complex. Okay, this is D of delta 0, okay? And there is one zero cell which corresponds to delta 0. So this is V delta 0. We can consider all the open cells which are adjacent to V delta 0. So all of these. Sometimes this is called the star of V delta 0. And if you take the boundary of the star, you get the link. So if D delta 0 is a PL manifold, a neighborhood of it should be a ball, and the boundary of the ball is a sphere. That's the idea. So what you really need to prove is that we have this degeneration. But you could wonder why there is any relation between this compact hyper-Kähler and the character varieties. So let me explain it. Yes?
I'm sorry, Rennie.
Yeah.
What is D of delta 0? Delta 0 is irreducible, right?
No?
Oh, so delta 0 is not a component of...
Oh, sorry. X0. Sorry, you're right. What is this? I need to... Okay, I mean, it's just to say that You're right. This should be X0. So the idea is that we have this degeneration, and on the central fiber we will have a DLT, a simple normal crossing divisor, and this is supposed to be a manifold. But if this is a manifold, a link of any point should be a sphere. Sorry, thank you for... So why hyper-Kähler manifold? So let's try to describe the first example, M1 GLN. So we are studying the representation of the fundamental group of a torus. So there are two generators. When I take a representation for each of these two generators, I need to give two matrices. But the generator of the torus commutes, so I need to impose the same condition on the matrices and quotient by GLN. So I can pretend that A and B are diagonalizable, but if I have this condition, they are simultaneously diagonal. It depends if you use the multiplicative or the additive notation. In the multiplicative notation is the same. I mean. So if I simultaneously diagonalize these two, what I need to remember to parameterize this space are just the eigenvalue of each of the two matrices corresponding to a specific eigenvector. So I need to remember the eigenvector, the eigenvalues of A, those are B, to the n. But you see, you are acting with GLN, so there is no order between the eigenvector. So actually, this is a symmetric product. So the symmetric product, so this is the product of C star to the n, quotient by the action of the symmetric product. So you see, this is a singular space, so there are no simple normal crossing compactification. So there is a natural compactification if you want here. You can take P2 and take the symmetric product. This is, of course, a compactification, but is not simple normal crossing. Not even if you small resolve, you go to the Hilbert scheme, it's not simple normal crossing. There are some strata which are non-normal. So, or even a DLT compactification. But at least it is local abelian. So the minimal model program tells you that you can find actually a DLT compactification of this space, taking some partial resolution of this compactification. But if you really want to compute the dual complex, you should keep track of all the strata of your divisor. And from that point of view, MMP is not constructive. So you just know the existence of this partial resolution. But you still notice that, at least formally, this remembers the way you construct the Hilbert scheme of the K3 surface. You take a symmetric product. So this is related to Hilbert scheme of K3. I think that in the GLN case, in the SLN case, it's even more evidence the relation. Oh. So what happens in the SLN case? You need to do similar computation, but now we need to force the determinant to be 1. So in the M1 SLN, this space is the fiber of the map C star times C star to the n. Of course, what I said before about the description of this space in terms of eigenvalues holds also here. But now you need to grant that the eigenvalue, these are the eigenvalues of A, these are the eigenvalues of B, and their product needs to be 1. So this is the fiber of this map over 1, 1. And if you consider the construction of the generalized Kummer variety, you perform the same construction, but you replace a C star times C star with an abelian surface. Well, here you obtain maybe the singular one. And again, here it makes sense to write a multiplication map. Okay. The way we make this correspondence formal is building that degeneration that I mentioned at the beginning. But in proposition A, I make a claim about the shape of the dual complex. So why hyper-Kähler manifolds should be related to that particular dual complex. So there is actually a conjecture in mirror symmetry that is related to that proposition. So the conjecture is that the dual complex of a maximally unipotent degeneration of hyper-Kähler manifold. So maximally unipotent simply means that the dimension of the dual complex is the dimension of the simple normal crossing itself. Okay? It can be phrased also in terms of monodromy, but this is probably the fastest definition. This should be PL homomorphic to CPN. So you need to think this as related to the fact that also the base of a Lagrangian fibration of the hyper-Kähler should be CPN. What do we know about this conjecture? Well, there is a result of Kähler, Saka, Laza, and Voisin. That says that the dual complex of X0 has the rational homology of CPN. And where this comes from, at least heuristically, so if you consider the Hodge diamond of an hyper-Kähler manifold, well, it will have this shape. And on this edge, you will see a partner of 1, 0, 1, 0. But this is precisely the rational homology of CPN. That's the relation between the two. Actually, there is another effective result So prescribing the rational homology is not enough for the conjecture, especially because you see our problem is proving that something is really a manifold. So you can have the rational homology of CPN but not being a manifold. That's the problem. So there is this other result of Brown and Mazzon. That says that actually the conjecture holds for spatial degeneration. What I mean here, degeneration of Hilbert scheme of K3 surface or generalized Kummer varieties induced by degeneration of the underlying K3 surface or the underlying abelian surface. Okay, and we would like to exploit this result. But you see that for the time being, we have statement just about hyper-Kähler manifold. We should make the character varieties enter the picture. And I would like to briefly describe the idea of the construction of the degeneration in the case of GLN. So, idea of the construction of the degeneration F, which is equivalent to our proposition, it was called A. So let's start with the degeneration. We say that we need to start with the degeneration of K3. So let's take a degeneration of K3 surface, the so-called dwarf pencil of quartic. This is given by an explicit hypersurface, but the idea of this degeneration is that, well, C is again a germ of a curve, so we will have a spatial point and a general one. On the general one, we will have a smooth quartic surface, so a K3 surface. And on the central fiber, we will have, so let's call it S. On the central fiber S0, we will have 4 components which are copy of P2. Okay, so in particular, if you remove from DI all the other strata, here you get C star times C star. And here is actually the core of the relation between S and C star times C star. Okay, once you have this, maybe once you have this, we try to construct in family the symmetry product. But there are some issues concerning the singularities. So, we can take this family and take the symmetric product in family. So what happens on the general point? On the general point, we will have the symmetric product of the K3 surface. And on the spatial one, we will have the central fiber, which will contain for sure a lot of components, new components, but one of them will be the symmetric product of the I, which is P2. And this contains inside C star times C star to the n. So inside this contains M1 of GLN. But it's not yet finished because here on the general fiber we didn't get the Hilbert scheme. So how far we are from an Hilbert scheme? We should take the Hilbert homomorphism. Which consists in a structure of a divisor E. But for the time being, we have done this on the general fiber. But now is where the minimal model program enters in the picture. You can do a so-called DLT extraction of E. So the idea is that you can compactify this general fiber to get a degeneration and now has the right singularity, the right central fiber, and now here there will be a lot of component on the central fiber, but at least one of them will dominate this other component. A standard minimal model, I mean birational geometry that say that this is a Crepin birational map. Well, let's say just birational. And so that the dual complex of this is the dual complex of the boundary of this. The degeneration here is on the spatial fiber induced by a degeneration of K3 surface. So the dual complex of the central fiber of this DLT degeneration will be CPN, following the result of Brown-Mazzon. But then the dual complex of this pair will be a sphere. So the dual complex of the compactification of this character variety will be a sphere as well. Okay, thank you very much for your attention.
Any questions? No questions?
I should answer a question. So the idea, how there is another conjecture, the so-called homological P equal W conjecture. If you go back to the diagram that I drew at the beginning, I had on one side let me just draw it quickly. We had M-dol on this side and MB and the Hitchin map. So you see, these two spaces are homomorphic, so they have the same singular cohomology. These spaces are fine, so in particular it carries a mixed Hodge structure. There is a weight filtration, W. On this other side, we have this morphism, so we can consider the Leray filtration induced by this morphism. That's not quite correct. Let's take a twisted version, the perverse Leray filtration, so the P. So a cohomological version of this conjecture should say that the way the geometry of this vibration is reflected in the geometry of MB is that the two filtrations are exchanged by this homomorphism. So what the P equal W, the geometric P equal W conjecture could inform about this cohomological conjecture is just the top degree. So the fact that the dual complex has the rational homology of the sphere implies that it is actually equivalent to say that the top degree pieces of this filtration are the same, just numerically. The commutativity of the diagram says that the first pieces of the filtration correspond. But since the statement is done up to homotopy, that's probably the only things that you can get. You need to refine the conjecture if you want to get more information.
thank you very much. So if there are no more questions, let's thank the speaker again.